Hello everyone, today we're going to talk about our topic, which is star classification. So to give a short overview of what we're going to be talking about, our primary goal for this project is to make it faster and more efficient for scientists to classify stars by type. And we're going to go into more detail of what type is and what kind of categories there are. But this would be dictated by the various metrics that the data supplies. And with our reliable system, there's going to be our goal is that there isn't going to be a huge amount of time that scientists will have to set aside to be able to go into each one of these stars and be able to determine the type. So with our model, scientists can simply feed the data into it, and they will at least be able to group stars quickly and more easily.
So for our data set here, we decided to go with this star data set to predict star types, which we found on Kaggle.com. It consists of 240 different data points, each star classified into 6 types. There are brown dwarfs, red dwarfs, white dwarfs, main sequence, supergiant, and hypergiant. And there's an even spread of 40 stars per each of these types. And the data set includes 7 features for each star. It includes temperature in Kelvin, luminosity in like number of suns. Radius is also in relation to our sun. The absolute magnitude, the type, obviously, which is one of the 6 types mentioned before, the color of the star, and its spectral class, which is sort of adjacent to color, but there's some difference there. And the dataset was initially designed for use with the Hertzsprung-Russell diagram, which is a technique for identifying stars, and it just shows that that technique is valid. For our exploratory data analysis, we have some charts here. Most of the stars were clustered around the lower end for temperature, luminosity, and radius, as you can see here. So they all have a pretty clear pattern, a lot of variance with the higher end. And then for the absolute magnitude, we found that there's a spread towards the outer bounds of the scales, far fewer in the middle. And for color and spectral class, we don't have any diagrams to show because they're not a numeric value. But around 70% of the color and spectral class were made up of the top 2 types. So for color, it was red and blue. And for spectral class, it was M and B that really made up the vast majority of them. And then there were around 70 to 80 other types that were just kind of a few for each one.
In our goals, our main goal was to make space exploration more efficient by allowing scientists to quickly and easily classify stars by type. Before starting on our project, we had to find a good data set. This was hard at first because originally we wanted to identify exoplanets, but no suitable data sets could be found. So we needed to find one that had enough metrics about stars so we were able to classify them and come to a conclusion about their type. Once we found a good data set, it was time to move on and find a good machine learning algorithm that fitted our needs. This ended up being logistic regression, the support vector machine or SVM, deep learning, and a rule-based approach.
So for the pre-processing of our data, it was fairly straightforward. We were just able to load it in, and it was all pretty well organized. However, there were 2 things that we had to do for it. There are 2 non-numeric features in the data. The star color, which is obviously things like red and blue, as mentioned before, and spectral class, which is one of 6 or 7 letters. For star color, we went ahead and used one-hot encoding, to get a bunch of columns to have numeric binary values of whether it was that color or not. And for spectral class, since there was a defined set of things that it could be, we used ordinal encoding instead to be a little more efficient and not just have 7 more columns for no good reason.
We had to study the dataset very, very carefully before formulating our rules, because each type of star had different characteristics like luminosity or temperature or radius, and we used these to be able to classify each star into a group and then distinguish the different star types. So as you can see in the code over here, I check here if the temperature is between 1,800 and 3,800. I check if the magnitude is greater than or equal to 16, check the spectral class and see if the color is red, and if so, then I return 0, which indicates it's a red dwarf. So basically I just followed this same logic for the rest of the types of planets, and this gave us 100% accuracy. Of the rule-based approach was that we were able to get 100% accuracy every time the program was run. There were a lot of cons though, however. This approach would not be suitable if the data set was much larger, as it would be impractical to go through the whole thing and check every metric and group them accordingly. Another con is that it took a very long time to implement as well. If we were using something more suitable like logistic regression or the support vector machine, which we'll get into later, then I'm sure it would have taken a lot less time to implement. We use TensorFlow and Keras to build our model. As you can see here, we use the ReLU activation function for our input layer and the softmax activation function for our output layer. Here you can see the input layer has 7 neurons and the output layer has 6. This number right here has to match the number of features that you have in your data set. We use the optimizer Atom, and I had to change the learning rate because our model was overfitting. So once I increased the learning rate a little bit, it definitely helped. And down here, this is where I actually train the model. So here I pass in the training data, and then I have 50 epochs. The batch size is 15, and here I'm sending in our validation data. And then I also had to implement early stopping to help with that overfitting issue.
To go into our next algorithm, we have support vector machine, and we thought this was pretty interesting because it's used for both classification and regression tasks in machine learning. And the primary feature that was more interesting is that it could be taken into a higher dimensional space based off the user that defines the kernel function, and this relates to the features that is presented. And we decided that there was no fine-tuning involved because the kernel that we used was linear and it already gave it a high accuracy rating when comparing from the prediction to the actual, and we'll get more into the comparisons between the accuracy, but for this algorithm it was 97.9% accuracy. And to go quickly into the coding section, it was really easy to implement. We decided to split the data into 80% training and 20% testing, and basically it's pretty self-explanatory. We used a SVM classifier to fit into the training data and then make predictions with that trained SVM classifier. And then after that, we evaluated the model's performance by getting the accuracy score and the classification report.
Our last machine learning algorithm we used here was logistic regression. We did do some fine tuning for it, and we looked at the number of iterations and the C value, which is the inverse of regularization strength. And we found that after around 2,700 iterations and a C value of 1.1, the model performs pretty well and doesn't take too long to run.
Of the metrics of these algorithms, as you can see, our rule-based approach got 100% accuracy. Again, this is not practical and it was really inefficient. For deep learning, we got around 96% accuracy, but the problem with deep learning is that the accuracy would fluctuate a lot. So sometimes it would be as low as 88%. For the support vector machine, we consistently got around 97% accuracy, and for logistic regression, we got an average of 95% accuracy. So as you can see here, for our rule-based approach, the precision, recall, and F1 score, they're all 1. For the support vector machine, here you can see we have almost 98% right there. Our F1 score is looking pretty good. An 88 there for the recall, and an 89, but only for one round of the precision. So for the weighted average, we get 98 across the board. For logistic regression, just a little bit off from support vector machine, but still doing pretty good. So as you can see, we get around 96 around the board as the score's weighted average. And as you can see, the accuracy here is also pretty close to 96%. And then for our deep learning model, we get 96% again. For round 0, the precision is only 0.83, but then for the rest, it's all 1s. The recall is looking a little low right here at 0.67, but then the F1 score is looking pretty good. A lot of 1s here as well. Percent accuracy. Before, like I mentioned, it was really time consuming to implement, and it would not work well with a large data set or something that had a lot of features. By far, the support vector machine, logistic regression, and deep learning were easier to implement. With deep learning, I did run into a lot of overfitting issues, so it took some time to remedy that. But logistic regression came out doing pretty well as also, but the support vector machine really beats everything in terms of its metrics and its ease of implementation. If it was easy to implement the rule-based approach and it was more reliable, then we would definitely go with that. But since it can't stand the test of large data sets, then we would definitely go with the support vector machine for a multi-class classification problem.
So in conclusion, we found that the support vector machine is the best model when it comes to multi-class classification problems on a very smaller data set. And this is kind of shown again as previously mentioned, like in the F1 score and the precision, the algorithm was simple and easy to implement. Although we also saw that the rule-based approach was testing at 100%, and we thought that was kind of interesting to see the contrast between what the context is and what algorithm is best used. And from this experiment, we kind of know now that how various machine learning algorithms are, and how to compare and contrast their performance as well, so that we can use the most efficient tool for the problem at hand. And that concludes our presentation. Thank you.